Guys, good morning. This is from yesterday. This is 7.5 acid-base chemistry and pH, your assignment from yesterday. So let's go ahead and look at that on our presentation. Okay, so let me get to that before you guys check out. So acid-base chemistry. Lesson summary. This is what you want to learn out of this from yesterday for your test, of course, for the unit, and possibly the midterm. Acids turn blue litmus paper red, taste sour, and react with metals to produce hydrogen gases. There you go. We're learning something, again, from your previous units. We have something reacting with metals to produce hydrogen gases. So things combine, and certain things combine to make something like an acid or a base based on what it is and what you see in the reaction. Common acids include vinegar, which is HC2H3, oxygen, and stomach acid, HCl. If you're still struggling with subscripts, that's HC sub 2, so there's 2 carbons, 3 hydrogens, and 2 oxygens. All right, so common acids, vinegar and stomach acid. Of course, which one do you think would be more acidic? And you would, definitely think that the stomach acid would be instead of the vinegar, because you can tell you pour it on your hands and it's not going to hurt. And we need to break down some very complex things. Bases turn red, litmus paper blue, have bitter taste, and are slippery to the touch. Well, this is probably the oldest trick in the book in chemistry. You do have other indicators that are a lot more specific. There are pH meters that you stick into the water or whatever you have, and it'll give you a digital readout of what it is. You do have other colors that can determine, that are more specific. Say, oh, it's blue as a base. Well, how much of a base is it if you don't know? And that kind of thing. So common bases include Drano, soft soap, milk of magnesia, and Windex. And you know that some of these are stronger bases than others. Okay? Milk of magnesia, if you don't know, is some type of stomach digestive helper with things that might not be going well with their digestive system. Strong acids and bases undergo 100% dissociation in water. All right, so things break apart, and a lot of hydrogens are floating around in that thing, and dissociation means splitting apart from. That's the hydrogens, dissociation, 100% strong acids. Acid-base neutralization reactions produce salt and water. The pH scale is based on molar hydrogen concentration. All right, so go back to that. Acid-base neutralization. So you're neutralizing an acid to make it more neutral. All right, you're taking a strong acid, pouring a substance like water. If that's a strong enough thing to neutralize it quicker, you can add other things to balance that out. You do also have buffers that help resist changes that you can put in there as well. The pH scale is based on molar hydrogen concentration. Okay, and there's ways to signify that with symbols. Brackets will give you concentration of. So P usually means concentration, and of course H is hydrogen. So concentrations of hydrogen ions, molar hydrogen concentration. That's what that really stands for. You have POH as well. Okay. Acidic substances have concentration of hydrogens or pHs above about 1 to 6, with 7 being neutral. That's your basic pH scale, if you've ever seen that in the past. I hope you have. Basic substances have pHs of about 8 to 14, being neutral. Now, if you look at the thing, the lower the numbers, you start with A in the alphabet, and you end with 14, and B is after. So you have acid first, base last after that, just like an alphabet sequence. Really quick, we're going to go through this. These are your vocabulary words. Just get to know those. Okay? Binary acids. What does that mean? It means two. Two acids. Or 2 elements making that acid. Dissociate means to break apart. Hydrohalic acid means a halide ion containing hydrogen. Halides, of course, are in your periodic table and exist in that same column. Hydronium, that's an H3O plus, which means it bonds. See how it's positive? It gains a positive proton. It's a hydronium. Okay, you have concentration of hydronium too, so sub P H3O. Indicator, something that tells you what the acid is, if it's a strong acid or where it exists. Now that litmus paper test that goes red or blue is not really a great indicator of how strong it is. And those indicators give you a strong, distinct color of change. Litmus paper, paper infused with a chemical dye, extracted from lichens, and which turn blue. Okay, so lichens is a type of plant-based thing, which most paper is made out of, as you know. And that usually is litmus paper base, blue, red, acid. Almost like acids can burn. Bases are not that great, some of them either. I've seen some bases burn through wood in my own shed, which was really great to find out one morning. Oxyacids, acids consisting of 3 elements, including oxygen and usually hydrogen. Strong acid slash base, they basically acid or bases that ionize easily, completely in water. So you have OHs representing the bases completely ionizing, OH negative, and the strong acids which have hydrogen ions dissociating and ionizing easily, H plus and OH negative. Okay, properties of acids. This is directly out of your content. Common properties, sour taste of acids. So properties of acids. You're probably most familiar with relation to citric acid, which is what makes lemons and other citric fruits or citrus fruits taste sour. Okay. Our taste buds are excellent hydrogen ion sensors. The fact that one of the primary functions of our taste buds is concerned solely with determining the acidity of what goes in our mouths underscores the importance of acids in our lives. Folic acids help create great brain tissue with infants. That's right out of oranges, and helps you develop good minds and brains and nerve endings and nerve cells. However, testing whether something is acidic by taste is generally not a good idea, especially in a lab setting. Trust me, I know. Better to test for acidity to use as an indicator. Indicators are substances that can be used to determine the relative acidity or basicity of a solution, generally through very distinct color changes. I prefer an actual pH meter that tells you exactly the number you're looking at. I've used that in an environmental science lab professionally and is more of a up-to-date indicator, but in a lab setting in high school, probably not used that often. They are out there. One common type of indicator is litmus paper. If a piece of blue litmus paper turns red when dipped into a solution, it means that it is acidic. Now, if the red litmus paper stays red, it's not basic, basically. So let's look at this.
While it is possible to quantitatively measure the pH of a solution using a device known as a pH meter, there are also ways to determine pH qualitatively. In this lesson, we will learn about indicators, which help us indicate the pH of a solution. An indicator changes color depending on the pH of the solution analyzed. Because of this, they are also known as pH indicators. Universal indicator is very versatile as it can measure pH across the entire scale from 0 to 14. It is not a single indicator, but rather a combination of various indicators. If you look at the color changes of universal indicator according to the pH of a solution, you will find that it resembles a rainbow. If universal indicator solution turns deep red in a solution, it means that the solution is strongly acidic, with a pH of 1 to 2. If the universal indicator solution turns green, it means that the solution is neutral, with a pH of 7. If the universal indicator solution turns dark blue or purple, it means that the solution is strongly alkaline. Universal indicator paper works in exactly the same manner. Litmus is another indicator commonly found absorbed onto paper as litmus paper. Blue litmus paper turns red under acidic conditions, pH less than 7. Red litmus paper turns blue under alkaline conditions, pH greater than 7. Phenolphthalein is an indicator commonly used to determine the endpoint of a strong acid, strong alkaline.
Phenolphthalein, and what you're seeing here is a lab that is usually performed in your first year, freshman year of college. It's called titration lab. So when you hear the word titration, you'll know what you're kind of finding out is the weakness or strength of the solution, acidic or basic, in that flask.
Alkali or weak acid, strong alkali titration. It goes from colorless to fuchsia pink at a pH of 8.2. Methyl orange is used to determine the endpoint of either a strong acid, strong alkali, or strong acid, weak alkali titration. It is red at a pH lower than 3.1 and yellow at a pH higher than 4.4. In conclusion, indicators are substances that change color at a certain pH. The point at which an indicator changes color is known as its endpoint, which can be at any pH. Common indicators that you will encounter are universal indicator, litmus in the form of litmus paper, phenolphthalein, and methyl orange.
Okay, guys, we're going to get back to the presentation. Great job. Thanks for that, Fuse School, and for that presentation. As you saw, there's a lot of stuff out there for you to look at. Another property, moving on, of common acids is reactivity with certain metals to form hydrogen gas. Now, you may be familiar with metal acid reactivity from the last two labs in this unit. 3 examples of metal acid reactions are shown below. That these are single displacement, we know what that is, or should, and of a pure metal reacting with an aqueous solution, and we know that, of course, by our subscripts of what that is. A solid zinc, we know it's a metal, and aqueous, that's kind of mixed in with hydrochloric, and a hydrochloric acid will be a mixture. Zinc chloride is what is coming out of that, another mixture, and your H sub 2, which is your hydrogen gas. So we're looking at a single displacement. We're bumping out that H, and there's 2 H's. We're substituting here or displacing that H with the zinc. And that's what you have. There's 2 Cl's. That is perfectly balanced. And this is the exact same reaction. You're just changing the letters here. Metal, metal, metal. Liquid, liquid, liquid. That's, one of your vocabulary words of what type of that liquid that is, or aqueous solution. And again, it's, of course, a halide oxide reaction there, halide. And then we have, of course, your zinc, magnesium, and barium. They're all metals reacting with the halide. All right, so there you go. These are some common properties of acids. I'm not going to read through these because you can take these down, memorize those things, and move on from there. One thing to point out, carbonates, you need to know what that is in the future. Citric acid, of course, we know that. Conductivity, of course, it's the movement or conduction of ions or electrons or protons down something. That's kind of why conductivity, using electrolytes from Gatorade, helps athletes or other folks stimulate good flow of nerve reactions to movements and things like that. Is that as Gatorade the end-all be-all of the electrolytes you need, or the things you need to recover or get better at what you do athletically? No. They always say that, now they're saying coconut milk, actually coconut milk with chocolate milk are a better recovery liquid. Good little piece of information for you. Even those that are thinking, not athletes, because it helps brain function as well, and recovering from tests and things like that is good to take in. Acids are divided into 2 groups: binary, which means 2 acid elements bind together, and oxyacids. You can kind of guess, oxyacids consist of 3 elements. One is going to be oxygen, and one is usually hydrogen. Okay, that looks like 2, but trust me, there's 3, because H2 is going to be there, and there's going to be 1 oxygen. H2O is one of them. Usually 1 hydrogen on binary acids like HCl and those kind of things. Usually a hydrogen, don't say always. Looking for another halide maybe. The chemical formula for any type of acid begins with 1 or more hydrogen cations. Okay, the anion, as we learned before, ends in IDE, such as chloride. All right, so name of binary acid depends on the anion, which ends with IDE, such as chloride, sulfide. The prefix hydro is there when you have a hydrogen cation before the name of the non-metal. Its ide ending is replaced by ic. Okay, well, remember those are suffixes that are used. This is the IDE suffix, this is the IC suffix. For example, acid HCl is named hydrochloric acid. Hydro is the prefix. Whatever acid or element you have, hydrochloric acid. Okay, the anion is chloride. Okay, so Cl negative. That's the anion, the negative ion. So the prefix hydro is used, and the IDE ending is replaced by IC. That was your naming of ionic bonds or compounds, or elements with ionic bonds. When the anion ends in ATE, such as oxy acids containing sulfate and phosphate, the ATE is placed by ic again. So we have this HNO3, all right, and we have the is named nitric. Sorry, I was going to say citric. Nitric acid, and the ion is nitrate. So the 8 ending is replaced by IC. So we have some differences there when we change the type of bonding we have there based on what they do. And this is naming the acids. Okay, moving on. List of some common strong acids, and I'm not going to read through this. You notice the names here are similar to what you just read about. And are these the only ones? No, they're lists of common ones, but I would probably put some 95% probability that these are the ones you're going to see in a lab setting in the future, in your labs and stuff like that. If you move on to a college chemistry type of a lab setting, these are going to be the things you're going to use. I didn't use the hydroiodic acid, if that's the way I think, hydroidic acid, sorry. I kind of stumble on words when I'm going fast to get through this. There's 20 slides. I don't want to take too much of your time. Naming acids, basically, I'll go through one example. Hydrogen fluoride, you have a hydrogen and a fluoride. You notice that was to be the ionic bond. If we're doing acid name, which you can do regular ionic bond name, but this is hydrofluoric acid, hydrofluoric, and they changed the IDE with an IC. All right, so there's your example. And that is a binary. These are oxy acids. Okay, so we're using the sulfuric instead of the sulfate. Okay. Properties of bases now. Okay, we're at the base, and going to bases. I'm going to talk like this now because we're in the base area. Bases are also a number of characteristic properties. Slippery is a good one to classify those. Bitter and that kind of thing. That's sour. Bitter compounds are basic. Caffeine, milk of magnesia, which is the digestive thing. You see that right there, the concentration of that stuff, are two bases that you may have had the opportunity to taste, although the bitterness is generally masked by the other flavors when the compounds are consumed. I take my coffee, without anything in it. I just take it off the pot, pour it in, and I go. I don't put the, fruit, the frothy stuff that Starbucks will put in there. Basically, you're drinking dessert, in my opinion, in the morning. Other common bases are found in a number of cleaning products. You got Drano, Windex, and there's others. Like acids, bases can be identified by the use of an indicator. All right, red litmus paper is dipped into a basic solution, will turn blue. It won't if it's an acid or not a base. And these are the common properties of bases, and you can read through those. Slippery, bitter, corrosive, Just because it's not an acid, and a lot of people use acid burns as an example of, oh, these, the corrosive also means these bases can do that. Corrosion means it's going to eat through metal, and it's going to burn through skin, or it's going to burn through wood. Now, remember that pH is greater than 7. 7 is going to be neutral, and then lower than that is acid. And it does react with acids to form salt and water. We saw that in some of your questions, and there was a question that a student notified me of that said they typed in the right answer and they still got it wrong. I'm going to have to review that one and see if everyone did that too. So here's some examples: sodium hydroxide, calcium hydroxide, some examples of some common things you probably will see with bases in the future. All right, so what that is, the base often ends with one or more hydroxide ions. You see this OH, OH, OH. Yeah, that's what you're looking for, and it's usually, okay. And ammonia is a little bit different. You'd see, okay, the H would be in front if it was an acid, usually. Hydrobromic acid, nitric, potassium hydroxide, and barium hydroxide. The reason that this is hydrobromic and not hydroxide is because you have some OH, just regular H characteristics, and not an OH characteristic. You see that IOH is a hydroxide. Just a single H is an acid, bromic acid, and you have a hydrogen, so it's hydrobromic instead of potassium hydroxide. Just a regular element name with the ending in hydroxide. Strong acids and bases, and we said some of this, and we know that they completely dissociate in a water solution to make it aqueous or just a solution. Strong acids fully dissociate. Many ions are produced, making the solution a good conductor of electricity. There are only 6 common strong acids, and those are the ones we talked about before. Strong acids or bases are those that completely dissociate. Those are things you can pick out of these paragraphs that will give you an idea. Now, this is an interesting one. On popular crime shows, this very chemistry was used for a method to cover up a crime, they should say. Hydrofluoric acid was used to burn through human remains and conceal what happened or where someone was found so the evidence isn't there. All right. Now, surprising enough, hydrofluoric acid is considered a weak acid. Hydrochloric and sulfuric acid, I use those in a lab, and pretty much when I was a young chemist in a professional setting, I burned through a lot of clothing. A lot of Swiss cheese sweatshirts and stuff like that were existing. So be very careful. Don't take that, don't stick it up your nose and sniff it. You got to do the waft thing, but you don't need to know. As long as you know it's sulfuric acid, just say, okay, where's the gloves? Where's the goggles? Where's the jacket? Let's not sniff this thing. All right, so there you go. Examples of those again. I think I duplicated that. Again, just to emphasize it. Hydrohalic acids containing halide ions. Okay, you'll see this. You have increasing acid and strength, and your question in the material was, these are the acids. What's the bond strengths? Take a look at that. What's the electronegativity of a halogen? And you see those are listed based on the halogen that is present. Br, Cl, F, and iodine as an example. And of course, the biggest electronegativity. We're increasing acid strength as we go up. So radius of an anion, and the anion is the negative ion, which is the one on the right, chloride, for example. And then the radius gets small. We have these, synthesize and apply what you know about strong acids, bond strength, ionic radius, and electronegativity to explain why hydrofluoric acid is weaker than hydrobromic. So why is hydrofluoric weaker than hydrobromic? Well, there's indicators. Look at 2.8 electronegativity, 4.0 electronegativity. Radius, boom, and boom. Just do the comparisons. The bond strength, it can't dissociate, all right, as much as the weaker bonds. So you're going to say, it can't totally dissociate as much as the other one can. All right, hydrogen power, pH. How much does the concentration, the P, concentration of hydrogen ions? Okay, and this is something you have to pick through. Sulfuric acid, battery acid. I've used that extensively in a lab. Be careful. Trust me. I notice your coffee area here. As we go down, stomach acids, lemon juice, vinegar is your acids. Then we get into the bases, seawater, milk of magnesia, household ammonia. Then we get really into the basic stuff that can actually, cause some issue with corrosion. Some things you might not be familiar with is the units here. A 1 times 2 to the negative 2 molar solution. I use this when I mix solutions in a chemistry lab. How concentrated or how many moles in a solution, the molar concentration, is M is a unit of concentration. I'll explore. And the next unit, so unit 8, we'll touch on that a little more, but I just want to introduce that quickly. And here you go with your Kahn Academy instructions. So that's 7 minutes long. I'm not going to go through that. But that is available to you if you go through your content, and you can look at more stuff on Kahn Academy. You see how they're doing this strong acid, strong base, combine H plus and Cl negative. I'm talking over this guy. All right, the cation and the anion, and the hydroxide and the hydrogen ion.
H2O. So water
you get a water and a salt.
Product would be what's left over. We have Na plus.
NaCl is your table salt. That's sodium.
So that gives us
so I'm going to move on from that.
Which is sodium chloride.
And you can watch that.
So this is an example of an acid-base
for the basic time here. This is going to be a long lecture. We're already up to 27 minutes. So this is your lesson summary. We should have learned about indicators, your common acids, what litmus paper turns into based on what you have. Common bases. Strong acids and bases undergo what in water? Acid-base neutralization reactions. Produces what? The pH scale. You should have a good idea of that. So what's the molar hydrogen concentration in that? When you do it. So how concentrated is it in that hydrogen ion concentration, your pH concentration of hydrogen ions? Acidic substances, 1 through 6, 7 being neutral, and basic substances, 8 through 14.
You might think the chloride anion could function as a weak base and take a proton from water. However, that's not really going to happen very well because the chloride anion...
All right, sorry, that guy was still talking, but hopefully you summarized this. All right, so the question of the day for the Lord of the Rings, the plot hole in the Lord of the Rings was if the Eagles could take the ring with the characters to Mount Doom and throw it in to get rid of the ring, why don't they just do that in the beginning? Saves 3 films and roughly 10 hours of film. Well, because they drew, answer to that is they drew them away. And they had the ability to fly in without getting disrupted. Thank you for watching. Hopefully we'll see you in the Shire this week, and we'll be in other places, of course. And I want to kind of thank you guys and thank those at VirtualSC, YouTube, and those videos that we've shown today. Kahn Academy, Catawba Ridge High School, where I'm housed usually, and you guys for doing all the work. And I can't thank you enough, and for those that have made these pictures and images available and that kind of thing.